Hey everyone, today we are going to talk about strong acids and bases. So the biggest thing about strong acids and bases is that they dissociate completely in water, okay? So that means that if we take a look as an example of hydrochloric acid, for example, that hydrochloric acid in water dissociates into two separate ions, a hydronium ion, H3O, and a chloride ion. It's not partial dissociation. It's not most of it dissociates. It dissociates completely, okay? And the definition of a strong base is the same, that, again, it's talking about completely dissociating, okay? Completely dissociating into ions. That's the significance of strong acids and strong bases, that they completely dissociate into ions. So some examples of strong acids and some strong bases: hydrochloric acid, nitric acid, sulfuric acids. Most other acids are weak, and a weak acid, of course, is just when the opposite happens, when not all of the ions dissociate. And here are some examples of some strong bases: sodium hydroxide, potassium hydroxide, and calcium hydroxide. And just like the strong acids, most other bases themselves are weak as well. So take note of what the strong acids are and what the strong bases are. So let's differentiate between dissociation and ionization of ions. So dissociation is when ions form when a chemical comes apart. So for example, sodium chloride melts to form sodium ions and chloride ions. Ionization, however, is when ions form when two chemicals react. So if hydrochloric acid is combined with water, you get the hydronium ion and you get the chloride ion. So that's the difference between dissociation and ionization of atoms or ions. Now let's talk about Ka. Okay, Ka tells you about the acid strength. Strong acids have high Ka values. A strong acid is an acid that completely ionizes. A weak acid is an acid that doesn't ionize completely. So if we take a look at what the reaction like that might look like, we get hydrofluoric acid plus water. We get a hydronium ion and a fluorine ion, but it's not a full ionization. So that's why the arrow in the middle is not just one that goes from reactants to products. It's reactants to products to reactants to products. It's not a complete ionization. Here's a very important thing to kind of keep in mind. There's a difference between strength of an acid and concentration of an acid. Okay, so difference between strength and concentration. If we're talking about strength of an acid, then the Ka value can kind of be shown the following way. If there's complete ionization, a strong acid is going to have a Ka value that's bigger than 1. A weak acid is going to have a Ka value less than 10 to the negative 3. And A moderate acid is going to have a Ka value between 10 to the negative 3 and 1. So that kind of says how we can take a look at the Ka value of an acid and determine its strength. Now, Kb is similar to Ka, except for B stands for base, whereas A, of course, stands for acid. The general reaction when involving a base can be written as the base plus water gives you the base plus the hydrogen ion plus OH minus. So Kb is found by taking the concentration of BH plus times the concentration of the hydroxide ion, all divided by the concentration of the base. It says it right here. We're going to get the base. So let's go ahead and we can do some examples here. So the first example, we're going to find the hydronium ion concentration and the pH of a 0.0065 molar solution of NaOH, which is a strong base, of course. Okay, so in order to go ahead and do this, what we have to remember is that, oh, didn't mean to grab my highlighter, meant to grab my pen, here we go. So the concentration of the hydronium ion times the concentration of the hydroxide ion is equal to 1 times 10 to the negative 14. Okay, so when we talk about sodium hydroxide and its dissociation, what we're going to end up getting is, we just closed, never mind. So what we're end up going to get here is, we are going to get our sodium ion, hydroxide ion, and water. And the important thing to note here is that if you look at the balanced chemical equation, that there is a 1-to-1 molar ratio between sodium hydroxide and the hydroxide ion. So that's important because we know the concentration of sodium hydroxide is 0.0065 molar. So that also gives us the same concentration for the hydroxide ion. Now, to figure out the concentration of the hydronium ion, we are going to use this relationship right here. That is key. So, the hydronium ion concentration is going to be 1 times 10 to the minus 14 divided by 0.0065, which is going to give us let's go ahead and figure it out. Okay, we got 10 to the negative 14, and we're going to divide it by 0.0065, and we get 1.54 times 10 to the negative 12. That's the concentration of the hydronium ion. Now, using the hydronium ion concentration, we can now find the pH. Since we know that the pH is equal to the negative base 10 logarithm of 1.54 times 10 to the negative 12. So we're going to go ahead and figure out that, and we're going to get a pH of 11.81. Okay, let's do a couple more examples. So this one right here says, if we have 0.456 grams of pure hydrochloric acid and it's added to enough water to make 0.75 liters of acid solution, find the hydronium ion concentration and the pH. So the first thing we want to do is we want to revisit what the molar mass of hydrochloric acid is. The molar mass of hydrochloric acid. So in order to do this, what we should be doing is we should be going ahead and looking at our periodic tables. And if we look at our periodic tables, what they're going to tell us is that chlorine weighs 35.45 grams and hydrogen weighs 1.01. So the molar mass of hydrochloric acid is 36.46 grams per mole. Now with that, we're going to figure out the number of moles of hydrochloric acid that we have. So we're going to take 0.456 grams and we're going to multiply it by 1 mole for every 36.46 grams. And of course, grams are going to cancel, giving us just moles. And so 0.456 divided by 36.46 equals 0.0125 moles. And because it's such a small number, we will carry 4 decimal places for this. We might as well. So that is the number of moles of hydrochloric acid. Now let's go ahead and find the molarity of it. So to find the molarity of it, we know that M equals N over V, 0.0125 divided by 0.75, and what we're going to get is 0.016 repeated. So I'll say 0.0167 molarity. Now, the thing is that for hydrochloric acid, we know that when we add it to water, we get the hydronium ion plus the chlorine ion. And again, the key thing here is that this is a balanced chemical equation, and there's a 1-to-1 molar ratio between hydrochloric acid and the hydronium ion, because That's important because it tells us that if we have concentration of 0.0167 molarity here, that we're also going to have the same thing here for the hydronium ion. So this therefore answers part A. Now for part B, all it's going to be is we know that the pH is equal to the negative base 10 logarithm of 0.0167. So again, we're going to use our calculators here, and what we're going to get is a pH of 1.78. So that gives us our pH of 1.78 using the hydronium ion concentration that we calculated on the left-hand side. So once again here for this question, what we did was we found the molar mass of hydrochloric acid. We found the number of moles by dividing the mass of our sample by the molar mass. And then we divided the number of moles by the volume of water, and that helped us give us a molarity of 0.0167 of hydrochloric acid, which happens to be the same concentration of the hydronium ion concentration, which answers part A. Okay? All right. Two more examples are here. So here we go. Find the pH of a 0.024 molar solution of the strong base barium hydroxide. So we're going to take a look at barium hydroxide. So barium hydroxide in water is going to give us barium 2 plus OH minus 2 OH minus plus water. And that's the key, is that there's two hydroxide ions there, because therefore if we have a 0.024 molar solution of barium hydroxide, then this is going to be 0.048 molars of the hydroxide ion. So now it does ask us to find the pH, so we do need to use our concentration here to go ahead and find what the hydronium ion concentration would be. And so, oops. Okay, so now the concentration of that hydronium ion is going to be 1 times 10 to the negative 14 divided by 0.048, and work out that calculation. And we get 2.08 times 10 to the negative 13. And then we can do the pH calculation over here. pH is the negative base 10 logarithm of 2.08 times 10 to the negative 13. Okay, so let's do that calculation. And when we do that, we should get 12.68. That's the pH of the 0.024 molar solution of barium hydroxide. And that leaves us with one more question here. Calculate the hydronium ion concentration. and the hydroxide ion concentration, if we have 10 mils of 0.4 molar hydrochloric acid, is added to 90 mils of H2O, also find the pH. So let's start off with understanding what we're looking at here as far as what we need to do. If we have 10 mils and we're adding it to 90 mils, then the total volume is going to be 100 mils, which is the same thing as 0.1 liter. Okay. Now we have to know though how many moles of hydrochloric acid we have. So we can go ahead and find that out because the number of moles is equal to the molarity times the volume. So the number of moles is going to be the molarity times the volume. So the number of moles is going to be 0.004 moles. And then we can use the molarity equals N over V. So we have 0.004 divided by 0.1, which is going to be 0.04 moles per liter. So that is the concentration of the hydrochloric acid. Okay, so now we can use that to help us find the hydronium ion concentration, the hydroxide ion concentration, and the pH. And what I'm going to do is I'm just going to move this up a wee bit here to make this work out so we can have lots of room. So the thing is that we've seen before, but we'll just go through this process again. If we have hydrochloric acid and we add it to water, what we end up getting is the hydronium ion, and we also get the chloride ion. The key thing to look at here is it is a 1-to-1 molar ratio with the hydrochloric acid and the hydronium ions. So with us having that 1-to-1 molar ratio, the important thing here is it indicates to us that not only do we have, not only do we have 0.04 molar hydrochloric acid, but we also have 0.04 molar concentration of our hydronium ion. So then that answers the first part to find the hydronium ion concentration. So we could check that off. To find the concentration of the hydroxide ion, we just take 10 to the negative 14 and divide it by 0.04. And when we do that, we get 2.5 times 10 to the negative 13. So that is the concentration of the hydroxide ion. And finally, it asks us to find the pH. So when we're finding the pH, we are using the hydronium ion concentration in order to guide us. So it's going to be the negative log of 0.04. Which gives us a pH of 1.40. So that is the pH of the hydrochloric acid. So there's some examples of some questions that have to do with strong acids and bases. Try and do some of the practice questions that are given to you, and make sure to ask questions if you have them.